Hello and welcome to this talk on synthetic data generation for minimum exposure navigation. My name is BapatPaffenrothCowlagi and I'm presenting this on behalf also of my colleagues Nachiket Bapat and Randy Paffenroth. We are all at the Worcester Polytechnic Institute in Worcester, Massachusetts, USA. So the motivation for this project is fairly straightforward and well understood. A lot of engineering systems like aerospace systems, like aircraft and spacecraft, are expensive to operate, which is why the amount of training data that we can get from these sort of systems is relatively scarce. The demand for these kind of data is very large. We need it for various different purposes. My own interest, for example, is in control design, validation, testing, and so on, or perhaps reinforcement learning. So the gap between the availability and the demand for this data is usually filled up by synthetic data generation. This is not a new concept. We have been doing simulations for a very long time. The standard practice is to set up some sort of a differential equation model for the evolution of a state variable, followed by some output model and some visualization. And a forward integrating numerical solver is used to evaluate this or execute this simulation model. Some system identification methods might be used to fit certain unknown or uncertain model parameters to whatever experimental observations are available. So this has been standard practice for a very long time, but it's not without its challenges. The challenges are, several, including the noise and disturbance characteristics in these type of models often tend to be fairly arbitrary, or they tend to be for mathematical convenience, like white noise, which is not realistic. The state space models themselves may also have a lot of simplifications and approximations, which may not often reflect the reality. So this is the standard practice. Now, on the other hand, we have seen a very large explosion in the science of computational data synthesis through generative artificial intelligence model, or games, as I'm going to shorten it. A game learns to map, roughly speaking, a uniform distribution of vectors to some sort of an output distribution that looks similar to a training data set, and that similarity is through some statistical metric. Now, this has been very well known, so we have widely known examples of these being successful in the regimes of text and image processing. So, for example, this image that you see on the right-hand side is of a human face that's completely synthesized, so it's not a photograph, and this is being generated by this StyleGAN model. So this has obviously been very, very successful in some domains where there is an abundance of training data, right? So a search of the literature, not exhaustive on this slide at least, reveals a lot of standard models that are used to construct these game architectures. For example, generative adversarial networks, usually for image processing, also diffusion models, variational autoencoders. The transformer architecture is what underlies the ChatGPT or GPT architecture, and so on and so forth. So like I said, this is not meant to be an exhaustive list. I'm just bringing this up to introduce the concepts. But in this talk, we'll focus on two of these models, and I'll talk about them in a little bit more detail later. So the scope of this work is fairly limited. We study the problem of synthetic data generation for environmental features relevant for autonomous vehicle navigation. In particular, we are interested in something called a threat field, which might represent some feature of the environment, let's say a weather pattern or some terrain that we'd like to avoid, and so on and so forth. The idea is the threat field is known to have some dynamics. If it's a weather pattern, you roughly know how the weather moves. There are some real world data observations of these things, let's say from historical data might be available. But the key here is that the volume of real world data is very small, or relatively small, at least in comparison to the image and text processing applications that we've been seeing. And the objective of this project is to synthesize such threat fields that are statistically similar to the threat fields that we observe and for which we know some dynamical equations. The motivation is that once you know something about this threat field, it's actually very easy to do minimum exposure path planning and or navigation, and that can lead to a very rich variety of applications in autonomous vehicle navigation. So having said all this, let's move on to a slightly more technical problem formulation, and let's look into the details of this work. The objective, again, is to generate samples of a spatiotemporally varying threat field. So here, this is a threat field that maps to the real vector space, and it maps from the spatial and temporal domains. We impose a structure on it, so that's our understanding, so to speak, of the threat field, and we'll impose a series structure that decomposes the spatial and temporal components. So this variable phi is essentially a spatial basis function vector that we fix, and the coefficient vector theta is what we assume has some sort of internal dynamics, we are going to assume for the sake of this paper that those dynamics are linear. In some sense, you can always do this just by wisely choosing the spatial basis function vector. So your coefficients turn out to be linear. But the important thing is this noise term, and we don't make any assumptions about the statistics of this process noise term. So we don't say it's going to be zero mean Gaussian or anything. We're going to try and learn that from the data. So if I try to visualize this sort of a threat field, so the C as a function of the space and over time may look something as an intensity map that changes over time. So this is a single threat field representing a single data point. So that brings me to data. Now, data is pointwise measurements of the threat field taken at a bunch of positions in the spatial domain. So these are, for example, grid points, and over over certain time instance over an interval of time. This eta 2 is measurement noise that gets added, and yet again we don't make any specific assumptions about the statistics of that measurement noise. We try to learn that from the data. So a single data point, datum, is a time series of observations of this kind, pointwise measurements with some measurement noise. So this is the training data set. The ND is the number of training data points that we have, which I'm going to assume is relatively small. So the problem of interest is that with this training data set and the equations, the governing equations that we had on the previous slide, we would like to synthesize a new data set that is hopefully abundant. So we can synthesize as much as we want, which speaks to the need for computational efficiency of this training process. And we're going to investigate generative AI models to be able to do that. So the proposed game architecture is what we call a split variational recurrent neural network. The split part is our principal innovation in this project. The SVRNN for short is based on the idea of a variational recurrent neural network. You're probably familiar with the idea of a recurrent neural network, and later on in this talk, I'll explain what the SVRNN is all about. Roughly speaking, it can be thought of as a combination of a variational autoencoder, perhaps that's more familiar, and a recurrent neural network. So the key idea that I'm going to emphasize later is that the split between the latent space of this SVRNN architecture allows us not only to learn from the data, but also from the governing equations. And it sort of makes it convenient to incorporate both while recognizing that the governing equations may not exactly match the data due to noise. So this is the general idea. But before I get too far into the weeds of all of these architectures and whatnot, let me present some results about what we have achieved, and then later describe the architecture to you. So the one thing that I will point out is, in the parlance of physics-informed neural networks, I think we can consider this SVRNN to be dynamics-informed. So there's no physics that we sort of capture immediately here, but the dynamics of the coefficient vector is what gets captured into the SVRNN. So let me talk a little bit about the results that are available from this model, and then explain what the model itself is all about. I'm going to discuss the results of some numerical experiments that we conducted. And for the scope of this work, the quote-unquote real world, which I put a star before, the real world data set is also produced synthetically. So there's a slight paradox until we can lay our hands on an appropriate actual real world data set. But basically, for the real world data set, to synthesize the real world data set that we can use, we essentially solve that ODE with a large number of randomly chosen initial conditions and some process noise. The phi, like I said, are fixed radial basis functions. We chose a small interval for solving the equations, but then we downsampled that with 1 second intervals, and then we chose 4 of those as the interval of time at which we are going to record the data. And then the grid size is pretty large, so it's 10 to the 4 of a 100 by 100 grid, and therefore each data point is a vector of 40,000 features, essentially. So we generate a large pool of data this way using many different initial conditions and process noise, and then choose a smaller data set for actual training of the models that we used. So we are going to present some results with ND equals 25 and 50. This is the number of training data points that we actually used. Now, we implement and compare 3 different game architectures. The proposed SVRNN, the split variational recurrent neural network. But to compare that, we also developed a different dynamics-informed architecture called the split VAE, the split variational autoencoder, and a purely data-driven architecture called the variational recurrent neural network. Essentially, the difference between these two is that one is dynamics-informed and the other is only data-driven. So we expect that the dynamics-informed one will learn better through a smaller number of observations. So that's something we see in plots like this one. So this is a visualization of the outputs of the three different models as compared to the training data. So this is a principal component visualization. So we plot the or visualize the first three principal components. The blue dots, whether they are hollow or filled, are training data. So essentially, this is the pool of training data that I mentioned. The pool is large, of which we choose a smaller number to actually use for training. So those are the filled dots. The big green dots is the data-driven VRNN, the variational recurrent neural network that doesn't know the physics of the problem. The red squares is the proposed split variational recurrent neural network. And these triangles lying out here is the split variational autoencoder. So that's another different dynamics informed architecture that we created just for the sake of comparison. And as this plot will show you, the SVAE is nowhere near the distribution of the training data. So what we're looking is some sort of a match or similarity between these various kinds of points. Now, there's only so much we can see in a visualization. So we also compared the statistical moments of these different kinds of um, uh, distributions that we created versus the training data pool. So this is the training data pool, and we compared the first four moments of the first three principal components. And what one can find is that the mean value of the training data pool reasonably matches well the mean value of the data from the VRNN or the SVRNN. Now, this is with 50 data points, right? 50 data points used for training. And the same thing holds true for the variance and the third and fourth moments as well. So as far as this particular result goes, both the data-driven VRNN and the split VRNN do reasonably well, and they reasonably match the training data pool. So there's not a lot to choose. But now let's reduce the number of training data points. So now let's only have 25 data points that we use for training. And now let's look at the VRNN. So this is the data-driven. So that's all the way over here as compared to the training data pool, which is what we're trying to match. The split VRNN continues to do well. So the split VRNN is here. That continues to do well. The SVAE, the split VAE, continues to do badly. It kind of doesn't show very well in this particular angle. But if you look at the statistical moments, it's fairly obvious that the split VAE is not even close to the training data pool in terms of closeness to the statistical moments. Now, the split VRNN and VRNN now show a distinct difference in the sense that the split VRNN is actually much closer in all moments to the training data pool. So, in this limited set of results, what we find is that the split VRNN model outperforms the data-driven VRNN model as well as the dynamics-informed variational autoencoder model when there's a scarcity of training data. So, the promise shown by this model is for low data situations. And obviously, this is not meant to be an exhaustive study. We're still learning many different things about this SVRNN model, but this is a promising new result that we'd like to showcase. Now, having said all this, I would like to now describe exactly what this SVRNN model is, and in fact, some of the other models that I talked about as well. So the last part of this presentation now is what all these game architectures are actually doing. From this point onwards, I'm going to assume that you know something about neural networks and how they're trained, and you're probably familiar with the idea of autoencoder, which has an encoder and a decoder. And the variational autoencoder is pretty similar in that the encoder's output space is the same as the decoder's input space, and the decoder's output space is the same as the encoder's input space, which is the same size as the training data. So the idea is that after training this variational autoencoder, we simply take the decoder and make it take samples from a standard normal distribution over its latent space, that is the input space, and make it map those samples to its output, which hopefully then resembles the training distribution. To be able to do that, however, we cannot map like a normal autoencoder. We cannot map every point in the training data to a unique point in the latent space. So that doesn't work out if you want to use this as a generative model. And in fact, then the idea is to map points in this training data set to distributions in the latent space. And that's the variational idea. So the loss function that is used to train this sort of a variational autoencoder has the normal reconstruction loss that essentially says whether the output matches the input. So that's the standard autoencoder. But it also has this similarity loss, which tries to make this normal distribution that maps the input to some sort of a distribution in the latent space as close to a standard normal as possible. Here, the phi and theta are the parameters of the two networks, the encoder and the decoder. P and Q are the conditional distributions. So that's the variational autoencoder. The main idea here is that each point is mapped to a distribution in the latent space. You're probably also familiar, perhaps, with the idea of a recurrent neural network. A recurrent neural network is essentially a dynamical system where the time-dependent state variable, HT, H for a hidden state variable, and its temporal evolution are both learned. So you don't know what the state is, you don't know how it evolves, but you have some time series data that you'd like to present. So it is intended for temporal sequences of inputs and outputs X and T. And it is composed of two layers: a recurrent layer, essentially a dynamical system, which has its own parameters that are learned, the weights and biases are learned, and an output layer, which is a fixed layer, that's not a recurrent layer. And then this output this recurrence mapping actually resembles exactly a dynamical system, as a control theorist or a controls engineer like myself is usually familiar with. So now we go to the combination of these two things, the variational autoencoder and the variational, or just the recurrent neural network, to come to what's called a variational recurrent neural network, VRNN, which is roughly speaking a combination of these two. So like a VAE, the variational recurrent neural network has an encoder and decoder, but like an RNN, it also has a hidden state. And the hidden state has a recurrence mapping that changes over time, or rather that changes the state over time. And basically, the idea is that the VRNN encoder approximates some sort of a distribution condition not only on the input, but also on this hidden state, right? So in the variational autoencoder, it only considers the input, the X, but now it considers both the input and the state. And again, the idea, like the VAE, is to try to make that as close to a normal distribution as possible. So that's that loss function over here. And then there is a similarity, or a reconstruction loss, like a normal autoencoder, which is over here. So, some of these ideas are perhaps a little bit better explained in the paper. I would like to get to the main idea that we have innovated in this paper, which is the split variational recurrent neural network. And the idea here is that, again, remember, we have scarce training data, but plenty of solutions to the governing equations, which we can just solve by direct synthesis. And what we'd like to ensure is some sort of a combination between these two. So we augment the scarce training data set X with synthetic data from solving the governing equations without any noise, right? So the difference between the solutions of the governing equations without noise and the data set is essentially the noise patterns or noise statistics that we would like to learn. So XS can be as large as possible. Essentially, you're just solving a differential equation. The way we accommodate these two data sets while also augmenting them with each other in some sense, is to split the latent space such that one part of the latent space is reserved for the real world data, whereas the other is reserved for the larger augmented data set. So here's a conceptual illustration of these two. So we hope that the real world data is somewhat close to the noiseless idealized data that we can synthesize just by solving the governing equations. And then we reserve one part of the latent subspace to accommodate the real world data. So, again, we can go through some of the math. I don't think we have a lot of time to do that, essentially, but I can show you the loss function that looks something like this. So the key part here is this extra term, which again is some sort of similarity loss functions as we saw in the variational autoencoder, but with this indicator function that decides where to put that, or to which of the two parts of the latent subspace to map that output, or to map that data point to, whether it belongs to the real data set or the augmented data set. So in the paper, you're probably going to find some additional details about the implementation of these models. So they're not exactly very deep models, just 2 layers in the VRNN and 4 layers in the split VRNN, and relatively small models were able to accomplish the task that we set out to do. So just to conclude this presentation, we developed this split variational recurrent neural network for synthetic time series data generation. When we know something about the time series in terms of dynamics, we don't assume exactly what the process and measurement noises look like, but this is suitable for problems where the training data are scarce and some knowledge of the dynamics underlying the time series is available. So the key idea here is that we augment the training data with noiseless solutions of the dynamical equations, and then we split the latent space of the variational recurrent neural network to accommodate these two pieces of the two pieces of the augmented data. Thank you for your attention, and obviously you can find the full paper in the proceedings of the conference, but also on this archive link that I have mapped out here. And please feel free to contact either one of us with any questions or comments that you may have. Thank you.